So we start a revision of unit number 2, unit number 1, that is spur gear. In spur gear, or you can say before spur gear, we discussed to transmit power between the two shafts or between two axes. There are different options like a belt drive, like a chain drive, and one more is a gear drive. The question is when gear drive is used, there are different criteria. Likewise, you can see here in a chain drive, we use chain drive whenever center distance between two shafts is small. If center distance between two shafts where we want to transmit power is intermediate, then chain drive is used. And if we require a positive drive, means there is no slip drive and center distance is small, then we prefer a gear drive. That's what a basic about power transmission, different power transmission devices I discuss. Now, these are the topics that we have to cover under this unit, or we already covered under this unit. Classification of gear, then gear to terminology, means different definitions we discuss. After that, law of gearing concept and velocity of sliding, its derivation. Next, concept of path of contact, arc of contact, contact ratio. Then interference and undercutting. And finally, minimum number of teeth on gear and pinion. After this also we discuss some concepts like rack shift and methods to avoid the interference, as well as force analysis of a spur gear. These are the points that already we covered during regular teaching. So, but basically gear is, you can say gear is a disc with teeth cut on its periphery in a simple language. So it is a teeth with it is a disc with teeth cut on its periphery. Nothing but a gear, and it transmits motions as well as power. We classified gears based on these three parameters. The first one is connecting pair. Hello.
Some students are not able to join.
How many students join now?
97.
101.
Yes, I seen 101. So why they are not able to join? I don't know. Okay, now fine. If they are not able to join, I will share this recorded lecture today. It is not like that. Means join होत नाही म्हणून absent राहत असं नाही. ज्यांना पॉसिबल आहे त्यांनी, ज्यांना पॉसिबलच होत नाहीये, तो काही प्रॉब्लेम असेल तर आपण बघू. बाकी ज्यांनी लेक्चर मध्ये राहा त्यांच्यासाठी मी रेकॉर्डिंग शेअर करेल, कारण मला वाटत नाही माझ्याकडून काय प्रॉब्लेम आहे. बाकीच्या लेक्चरला असा प्रॉब्लेम होतोय का?
हो सर, ते 100च्या वरती जात नाही काही काही.
100 लिमिट आहे.
बरं ठीक आहे. ऍक्च्युअली तसं व्हायला नाही पाहिजे. बरं ठीक आहे, त्याबद्दल आपण जास्त बोलू नये आता. ज्यांना तुम्ही मेसेज द्या, इफ यू आर नॉट एबल टू जॉइन, आय विल शेअर रेकॉर्डेड लेक्चर इफ पॉसिबल. ओके, विल कंटिन्यू नाउ. आता जे लेक्चर मध्ये त्यांनी लेफ्ट करू नका, अदरवाइज मग परत प्रॉब्लेम होईल. ठीक आहे. सो वी आर डिस्कसिंग टॉपिक ऑफ गियर. हा येस, इफ एनी डाउट, अदर एनी डाउट, यू कॅन जस्ट don't text me because I'm not able to see that chat box. You ask me live session. Okay. Next, so we discuss gear classification. Here the gears are classified on three parameters based on how shafts are arranged, like parallel shaft gears, intersecting shaft gears, and non-parallel, non-intersecting shaft gears. So first, the classification is parallel shafts. Whenever gears are mounted on parallel shaft, there are three types, basically spur gear, helical gears, or sometimes called as herringbone gear, when it is actually herringbone means double helical gear, then rack and pinion gears. So these are three types used to transmit power between two parallel shafts. While to transmit power between intersecting shafts, the gears are bevel gears and helical bevel gears. While to transmit power between non-parallel, non-intersecting shafts, the gears used are spiral gears, worm and worm gear are the types used to transfer power between non-parallel, non-intersecting shafts. So this is basic classification we made based on the shaft arrangement of gears. Now here already we discuss a one by one discussion, a brief discussion about each gear. So I will not discuss this now as in detail because in unit number 1 and unit number 2 we are going to discuss different gears like spur, helical, bevel in detail. So at that time this will be discussed. So spur gear is spur gear, helical gear, double helical gear, and then these are the types of parallel shaft gears, including rack and pinion, while worm gear, then spiral gears, bevel gears. So these are the types of gears that already we discussed in classification. Next topic is important one is terminology of spur gear. in a theory examination or in MCQs, this topic can be asked. So what are the different types? What are the different terminologies that we seen for a spur gear? You can see the first one, important one is pitch circle. So pitch circle, you can see, okay, you can see this diagram. The pitch circle is imaginary circle. You can see this one is a pitch circle. This arrow is visible. Hello.
Yes, sir.
Yes, sir.
Okay. So this pitch circle is imaginary circle which transmits power by means of pure rolling motion. So you can see imaginary circle which by pure rolling action would give same motion as actual gear. So it is imaginary circle which by pure rolling motion gives power as that of a actual gear, or you can say gives same motion as that of actual gear. And all terms, other terms are defined with reference to pitch circle. So first we define pitch circle, and then with reference to this pitch circle we define different terms. Which different terms we seen? Now see, if you remember, while discussing this topic, I make some parts of this term. I make some section of this terms. So first one we define all terms related to pitch circle or related with pitch circle. So first one is circular pitch. Now what is circular pitch? Let's say this is one gear tooth and it is another gear tooth. If I consider a distance between this point, I hope arrow is visible. Yes.
Yes, sir.
Because otherwise, if that arrow is not visible, what I am showing it is not clear to you. So if I consider this point on this pitch circle here, and the corresponding point, corresponding means a similar point on adjacent tooth. I hope you understand meaning of adjacent. So if I consider this point and adjacent point on next gear tooth, and if I calculate, if I measure distance between these 2 points along a pitch circle, then the distance is called as circular pitch. So circular pitch is nothing but distance between corresponding points on adjacent teeth measured along a pitch circle. Circular pitch. Then you can see if I calculate width of the gear tooth or thickness of the gear tooth along the pitch circle, it is very important to define it along the pitch circle. Then the distance or width is called as the tooth thickness, and distance between the two consecutive teeth or space between two consecutive teeth, if I calculate along the pitch circle, it is called as the width of space or tooth space. So width of space or tooth space is distance between or space between two adjacent teeth measured along a pitch circle. So I define here circular pitch, tooth thickness, width of space, and all these are along the pitch circle. Another you can see, this is a pitch circle, and if I seen one circle also passes through top of the gear tooth. So circle which is concentric with pitch circle and passing through top of the gear tooth is called as an addendum circle. Similarly, a circle which is concentric with pitch circle and passes through bottom of the gear tooth is called as a dedendum circle. So addendum circle, pitch circle, and dedendum circle. One more is there called as a clearance circle. All are concentric circles. Now clearance circle is nothing but distance circle which passes through clearance point. Okay, that I'll discuss later. So these circles we seen addendum circle, dedendum circle, pitch circle, and some terms like circular pitch, tooth thickness, and width of space. Next one, if I now we'll see, we just considered along the pitch circle. Now next part, next section we'll discuss along the radius. Which terms are there along the radius? The first term you can see, if I calculate a radial distance between addendum circle and the pitch circle, then it is called addendum. While if you calculate distance between pitch circle and dedendum circle radially, of course we are seeing now terms radial in a radial fashion. So a radial distance between the pitch circle and dedendum circle is called dedendum, while distance between addendum circle and pitch circle is called addendum. So addendum and dedendum are the new terms I just introduced with you. And next one, if I calculate these two, if I calculate distance, or if I sum this, if I make summation of addendum and dedendum, then the distance is called as a radial distance is called as a total depth. So this distance is nothing but a total depth. So total depth is nothing but addition of addendum and dedendum. Now we'll see next term, that is clearance. And to define clearance, we need to understand, if you consider this is the space between the two gear tooth. So in this space, the mating gear is in mesh with this gear tooth shown. So here it will be a mating gear. But if you see in this, let's assume it is a mating gear tooth profile. So this gear is in contact with this gear shown, but it is not make contact at the bottom of the gear tooth. But there is some space. So this will be a, I'm saying this is a mating gear tooth. I'm showing with a highlighter. Is it visible?
Yes, sir.
Okay. So you can see here, there is some space, or there is some space is kept between top of the mating gear and this bottom of the gear we discuss, gear we consider. So that space is called the clearance. So if I calculate distance radially between two mating gears, then that distance is called the clearance. And if you pass the circle through this point, then it is called the clearance circle. In other words, we can say, if I subtract this clearance distance if I subtract this clearance distance, so this distance from total depth, that distance will be a working depth. So I define one more here. So this one is called the working depth. So total depth minus clearance, this clearance is nothing but a working depth. So we define total depth, working depth, clearance, addendum, dedendum in second part of terminologies, which are along the radius. Next part is along the axis. So when we see along the axis, the portion of the gear tooth profile above the pitch circle is called as a face, while portion of the gear tooth profile below the pitch circle is called as a flank. So if you consider, now I'm measuring distances, I'm defining terms along the axis. So you can see here now, let's say this is your pitch circle. If I seen it along the axis, and here it is now for the same also for this gear. So portion of the gear tooth above this pitch circle So this above this pitch circle is called face, while below is called as a flank. You can see here, this portion is called face, while this will be a flank. So this one, showing here this will be, this one is a face. Above this is called face, and below this is called as a flank. So this whole portion I'm saying, you can see like this. This one is face, and the below one is a flank. So we define face and flank along the axis. Now this top portion is called a top land. We'll not waste more time now here. This top portion is called a top land, which is shown here. Of course, it is measured along the axis. And this bottom portion is called the bottom land, which is shown here, you can see. So top land, bottom land. And the last one, we can say a face width. Now, if we calculate width of the gear tooth along the axis, it's called the face width, which is shown here, you can see. So if you can consider, if you calculate width of the gear tooth along the axis, it is called the face width. While if you can calculate width of the gear tooth along the pitch circle, is called the width of space. There is difference between width of space and face width. So this is all about gear tooth terminologies that we define. Any doubt here on gear terminologies? Along with these terms, we also define some formulas like a circular pitch. Already we define what is circular pitch. It is distance between corresponding points on adjacent tooth when measured along a pitch circle. That is a circular pitch. And in mathematically, we can define circular pitch as circular pitch is equal to pi d by t. This is formula, and d by t is module. So it is nothing but pi into m. Circular pitch is equal to pi into module. That is the formula. Then diametral pitch. Diametral pitch is nothing but reciprocal of module. What module is? It is ratio of pitch circle diameter to number of teeth. While diametral pitch is the ratio of teeth to the pitch circle diameter. So these two are reciprocal of one another. That is diametral pitch and module. And other terms already we defined. One more term just remaining, that is backlash. What is backlash? It is difference between tooth thickness and tooth on circular pitch. Means what? We will see here. Difference between tooth thickness. So you can see there is space between the two mating two adjacent teeth. That space is called the width of space. And when another gear, like say here, it is in mesh with this gear, then difference between tooth thickness of mating gear and this width of space is called as a backlash when calculated along the pitch circle. So along the pitch circle, this difference I'm saying is called as a backlash between the tooth thickness of the mating gear and this width of space is called backlash. Ideally, it should be 0, but practically some backlash is provided to allow thermal expansions. Okay, now other terms like a path of contact, length of contact, that we discuss later on. So next one is a law of gearing. Okay, so we just completed gear to terminologies, different gear to terminologies. Next important topic that we have to discuss is a law of gearing concept. And for understanding this, this slide is visible to you.
Yes, sir.
Okay. I hope you remember this diagram. What it consists of, we consider two gear tooth profiles, a random gear tooth profile selected. We must draw this diagram by understanding. First, I consider two gear tooth random profiles. Let's say having center distance O1, O2. So about O1, I consider a pinion rotating, let's say clockwise, and wheel rotating anti-clockwise. So O1, O2 is center distance. Assuming that omega 1, the first pinion, is rotating with angular velocity omega 1, and this wheel is rotating with angular velocity omega 2. Next, we consider these gear tooths are making contact at point of contact Q, and the P is pitch circle. Sorry, P is a pitch point, which is a common point of the two pitch circles. So PQ is nothing but a distance between pitch point and point of contact. If you consider, so PQ is distance between point of contact and a pitch point. While if you consider this point of contact, and at this point of contact, if you drawn a common normal, so Mn is common normal to this point of contact. Actually, it is nothing but Mn is common normal to the gear to surface, this mating surface, through point of contact, because we can't draw a normal to a point, it should be to a profile. So to mating profile, we draw normal, and through point of contact, that normal, common normal is, we can say common normal to point of contact or through point of contact is Mn. So if Mn is common normal, then Tt is common tangent. So I repeat again, I consider two gear tooth profiles, random section with angular velocity omega 1, omega 2, having center distance O1, O2. Then I consider Mn is common point of common normal, while Tt is common tangent. Now, what law of gearing is? If you want the gear teeth to remain in constant in contact, then the component of velocities along the common normal must be equal. Actually, this is condition. But why it should be equal? Because we know, actually, law of gearing means if the two gears, we know that gears are used to transmit a constant angular velocity ratio. That is omega 1 upon omega 2 must be constant. And if these two are to be in constant, then we have to prove that the common normal through point of contact must pass through pitch point. So what happens if this common normal through point of contact, that is Mn, passes through pitch point, our angular velocity ratio remains constant. We have to prove through this derivation how that angular velocity ratio remains constant. So I'm just telling you what is law of gearing. That is to maintain constant angular velocity ratio, the common normal through point of contact must pass through pitch point. That is our basically a theorem. And to prove this, what we consider two velocities. Let's say v1 is the velocity of point of contact q, where considered on point O1, while v2 is velocity of point of contact q when considered on gear 2. So v1 and v2 are the velocities of point of contact when they considered on gear 1 and 2 respectively. So if the v1 and v2 are known to us, then I can find out a velocity along the common tangent as well as velocity along the common normal. So for a pure rolling motion, these two gear tooth must slides along a common tangent but not along common normal, and hence along common normal, if I find out the components of these velocities, they must be 0. As you can see, v1, the component along this common normal is v1 cos alpha, while component of v2 is v2 cos beta, as alpha and beta are the angles made by v1 and v2 with common normals. So if I find out the relative velocity, it must be 0. So v1 cos alpha minus v2 cos beta must be 0. So it will is equal to 0, means v1 cos alpha is equal to v2 cos beta. So relative velocity along common normal must be 0. That is what our start of the derivation. If I consider this and then go on putting this value like v1 and then the alpha term, that is cosine terms, finally we'll prove that this angular velocity ratio, that is omega 1 upon omega 2, is equal to O2n upon O1m. Now what is O2n and O1n? You can see O2n is normal to this common normal drawn through center of rotation. Similarly, normal to common normal through center of rotation of first gear is O1m. So O1m and O2n are the normals drawn to common normal. And as it is equal to O2p upon O1p, as p is a fixed point, we can say that as this ratio is constant, means we can also prove that omega 1 omega 2 also remains constant. So we finally proved here how this angular velocity ratio is constant, but when it will only when this common normal passes through pitch point. So it's just simple derivation. Start with and how to start, I'm telling you. Just start with the relative velocity along common normal will be 0, and then just put value of v1 v2 and alpha cos beta. That's what. So simple derivation. Start with relative velocity of this common point of this point of contact along the common normal will be 0. Will get your expression. So this is all about velocity of sliding. Sorry, about law of gearing. What we discuss here, we consider two random profiles rotating with velocity of omega 1 omega 2 angular velocity with centers O1 O2. Then we consider common normal, common tangent, then its velocities and its relative velocity along the common normal. We consider put value of v1 v2 and cos alpha cos beta. We can prove that this angular velocity ratio remains constant. That is all about law of gearing. With the same note, we can see also concept of velocity of sliding. As we discussed in the previous session, that is in the derivation, as this common normal or velocity along the common normal will be 0, but this relative velocity along common tangent, it will not be 0, or it will be some component. It is having some value. So to determine or to express velocity of sliding, we have to consider relative velocity along common tangent. Remember, for law of gearing, we consider relative velocity along common normal, while for velocity of sliding, we have to consider along a common tangent. That is a start of the derivation. Then further we can easily modify it, easily prove it. So first I consider it is the velocity of one tooth relative to meeting tooth along the common tangent at the point of contact. So this velocity is not 0. So that we need to find out how much it is. So Vs we need to find out. Vs means velocity of sliding. It is nothing but velocity of one tooth relative to meeting tooth along the common tangent at the point of contact. And for this again we consider same expression, that is we consider v2 sin beta minus v1 sin alpha. Now here v1 v2 makes alpha beta with common normal, and hence it makes 90 minus alpha 90 minus beta with common tangent. Hence his component is sin alpha sin beta with common tangent. If cos with common normal, sin with common tangent. So again same expression, Just consider Vs, put value of V2 and V2, put value of sine beta, sine alpha. We will prove that this Vs is equal to omega 1 plus omega 2 into Qp. That is our final expression for velocity of sliding. Now what this expression is, Vs is equal to omega 1 plus omega 2 into Qp. This is our simple derivation. Actually, just we put value of Qp and Pn. That will not discuss now, but okay. So finally, we get this expression, and this expression is nothing but, you can see here, velocity of sliding depends upon sum of the angular velocities and distance between these 2 points. What is this point? Basically, Qp. Q is point of contact, and P is pitch point. So velocity of sliding is depend upon point of contact, that is Q, and pitch point, that is P. So it is directly proportional to Qp distance as well as sum of the angular velocities. Now we know that the point of contact, here we can say it is point of contact point P. So point of contact can be at any point. When point of contact is at Q, it will be this distance. When it is at P, it will be 0. When it is somewhere other distance, it will be E. So this point of contact is changed, and we can find out velocity of sliding at different points when this gear 2 are in meshing. Okay, so this is about velocity of sliding. The next topic we discuss is types of or forms of gear teeth, like a conjugate teeth, cycloidal teeth, and involute teeth. The first one is conjugate teeth. So we also discuss in the experiment when gear teeth are called as conjugate teeth. Basically, whenever the two gear tooth profile which satisfy law of gearing is called as a conjugate teeth, the profile is called conjugate profile, and that action is called as a conjugate action. But as we've seen while discussing conjugate profile experiment as well as here in theory, as these profiles are randomly selected, it is difficult to manufacture this kind of profiles. So there is difficulty in manufacturing as well as the cost of standardization is higher, and hence the production cost will be higher. Hence these conjugate profiles are not generally used. But instead of that, some other profiles like involute and cycloid profiles, which are easier to manufacture or which are standardized, are used in actual production. So here we discuss concept of conjugate action, conjugate profile. So gear tooth profile which satisfy law of gearing are called conjugate profile. Their gearing action is called conjugate action, and their profiles are called as the conjugate profiles. That is concept of conjugate profile and action. The next one is, you can see here, this will be a tooth profile, and this one is involute profile. We seen one experiment, that is procedure to draw an involute gear tooth profile, to generate an involute gear tooth profile by using a rack cutter. This kind of profiles we obtain in the experiment number 1. And this one is a cycloidal profile, a cycloidal curve. We know how it is drawn. Basically, whenever a circular disc is allowed to roll over a flat surface, a straight line profile, then it is called as a cycloid. But cycloid is of two types. One is epicycloid, other will be a hypocycloid. So when we call it is a epicycloid, whenever this kind of gear tooth profile, this one circle is allowed to roll over another circle, then point on its periphery of that outer circle will generate a curve called as a epicycloid. And the nature of epicycloid is shown here. While whenever this circle is allowed to roll inside the circle, then that profile is called as a hypocycloid. So this one is a hypocycloid. So there is difference between epi and hypo, but both are types of a cycloid. As circle is rolling over a surface. Now surface may be circle. If it is a circle, that is used to draw a teeth of a gear. While if that surface is a flat surface, a straight line profile, like here, this one. Then it is used to draw a rack teeth, as it is rolling over a straight line profile. So we discuss a simple concept of cycloid, epicycloid, and a hypocycloid. The next one is involute profile. How it is drawn, we know that if I consider a thread is wound around this a circular disc, if I unwound that thread by making it tangent at every point, then end point of the thread will trace a involute curve. You can see this curve drawn is a involute. So this point, if I unwound it by keeping it tight like this, then end point of that thread will trace a involute profile. So likewise, this is also involute profile. And a circle over which that involute profile is drawn, the circle is called as a base circle. So in this case, this circle is called as a base circle, over which a involute curve is drawn. Remember the profile of the gear tooth. You can see this is profile of the gear tooth. Up to this, we can see that can be used to generate the gear. So this kind of gear tooth, the profile above the base circle is called involute, while profile below the base circle is non-involute profile. That thing we have to notice. Again, it is shown in the same way how involute profile is drawn. This is basically involute curve. That kind of gear tooth we seen in the rack cutter, which is used in experiment number 1. Yes, consider now how the profiles are drawn. If the circle is allowed to roll over a flat surface, in this direction it is drawn, a face portion is drawn by epicycloid, while plank portion is drawn by hypocycloid. Whatever we are discussing here, face, plank, whether face is drawn by epicycloid or plank is drawn by hypocycloid, all these concepts can be asked in a online or in MCQ can be asked on this topic. So we must know basic things. So we see here how this epicycloid and hypocycloid concept is used to draw a gear tooth profile. So face is generated by EP, while plank is generated by hypo. And when these circles are roll over a straight profile or a straight line, they're used to cut a rack cutter. They're used to draw a rack gear tooth. While here, when over a again circular portion, then it is used for a drawing a gear tooth profiles. So these are the gear tooth profiles, cycloidal gear tooth profiles, and here it is a cycloidal gear tooth profile for a rack. This is the involute profile. I just told you, if I unwound that string by keeping tangent at every point, tight at every point, then end point will trace a involute profile. That force analysis we will discuss later, but okay, we discuss one thing here. The tangential forces, there are two types of forces here basically, a tangential force Ft and other force is Fr in a spur gear. That radial force will try to separate the two gears, but tangential force is responsible for a power as well as torque transmission. And how it is given? So torque exerted on gear shaft is equal to tangential force into radius. So this is Ft into this R. It gives you torque, and hence we will be able to find out a power. Once Ft is known, we can find out F as well as Fr in terms of F. We can find out, provided that pressure angle phi is known. So Ft is equal to F cos phi and Fr is equal to F sin phi, a simple relation that can be used for a force analysis of a spur gear. This we will discuss later. Difference between cycloid and involute, this is theory topic we will discuss later, or you can go through this. There are 4 types of gear tooth systems: a 14.5 composite system, 14.5 full depth system, 20-degree full depth, and 20-degree stub involute. What these 4 types are already we discussed. If you remember, in these first 3 types, addendum, dedendum, distance remains same. While in the last type, it gets changed. And if you see carefully, in first 2 types, pressure angle is 14.5, or in last 2 types, the pressure angle is 20 degree. So the pressure angle is either 14.5 or 20 degree, and whether it is composite or full depth, accordingly, these types are classified. So this one is first type, that is 14.5 composite. Now composite means what? You can see first one is composite and full depth. Composite means this gear tooth profile consists of combination of involute and cycloid. At the top, these portions are curved, while in between it is a straight portion. So this middle portion is involute profile, while the upper and this bottom portion is cycloid. As it is combination of involute and cycloid, hence it is called as a composite system, and the pressure angle is 14.5 degree. So this angle is 14.5 degree. This one is circular pitch. You observe here, addendum distance is equal to 1 module, while dedendum is equal to 1.157 m times module, and this specifications are fixed. So if we are going to use a 14.5 degree composite system, then its module will be equal to 1 module. That is, addendum is equal to 1 module, and dedendum must be 1.157 times module. Next one is a 20 degree full depth system. So here we consider 14.5 degree composite. Next one is actually two systems are shown here. That is 20 degree full depth and 20 degree stub involute. So in 14.5 degree it is composite and 14.5 degree full depth. So difference only here, in 14.5 degree full depth, instead of this combined profile, it is a complete a straight line profile like this. So it is complete straight line profile is there, full depth involute. Only the change is pressure angle is 14.5. So if the pressure angle is instead of 20, it is 14.5, I can say the system as 14.5 degree full depth system. But as the pressure angle is 20 degree here, hence this one is a 20 degree full depth involute system. This diagram I am saying. So first three, that is 14.5 degree composite, 14.5 degree full depth, and 20 degree full depth are the systems having addendum is equal to 1 module and dedendum is equal to 1.157 times module. But in order to avoid interference, so teeth are reduced, addendum is reduced by some amount, as well as dedendum. How much it is? So addendum in stub system, now 20 degree stub involute system. Stub means modified system. In that system, addendum is 0.8 times module and dedendum is 1 times module. So these are the changes. So the first three having same dimension, while last there is some change. It is modified system. As it is modified, it is called as a stub, means short, like I'm saying, or I can say modified involute system. And the pressure angle is 20 degree. His name is 20 degree stub involute system. These are the four types of system that we discuss. A numerical, or not numerical, I'm saying, but MCQ can be asked on this topic. Okay. The next topic is path of contact, arc of contact. Which other lecture है? Next lecture is there?
Oh, sir.
Uh,
Sorry, sir. Answer.
okay.
Yes, sir.
Okay. Okay. We'll just end in 5 minutes. Path of contact. So what is path of contact? Diagram is in front of you. If you remember, we discussed this concept like O1, O2 are the centers. Then pitch circle radius is R. Addendum radius is R suffix A. We use small notation, that is small r, small ra are for the pinions, while capital R and capital Ra for gear. Phi is the pressure angle. And what is this K, P, L, M, N? Anyone can tell me? At least for some time. What is P?
Which point?
What? No, P is pitch point. Okay. K and L. Actually, KL is nothing but KPL. We can say KPL is a path of contact. So, what is path of contact? Basically, it is a path traced by. Okay, I will explain first this diagram. Already we should discuss many times. It consists of a base circle. This is a pitch circle, and this one is the addendum circle. So, the pitch circle, addendum circle, and the base circle. If I draw this common tangent will cut the portion of the common tangent. I'm saying the common tangent is MN, common tangent to base circle. You can see this. As well as this nothing but it is, we can call this MN as common tangent to base circle. It is tangent to this base circle of the pinion at point M and tangent to base circle of the wheel at point N. Hence, it is called as a common tangent to base circle. At the same time, it is also called as a common normal to point of contact, through point of contact. The point of contact may be K, may be P, or it may be L. So the portion of the common tangent, that is MN, cut by addendum circles is nothing but a path of contact. Now which portion is cut by addendum circles? You can see here, addendum of this wheel is cutting this common tangent at point K, while addendum of the pinion is cutting this common tangent at point L. So this KL is called the path of contact. So you can see here, it is length of the common normal cut by addendum circles of the wheel and pinion. So KL is path of contact. In other words, we can say it is path traced by point of contact of two teeth from beginning to end of engagement. Assuming that the point of contact begins at point K and during meshing, it will end at point L. So it is the path traced by point of contact from the start or from beginning to end of engagement. Nothing but a path of contact. So we can see the point of contact is K here. The notation may be K or Q we use, and it will proceed from K, P to L. So point of contact begins at point K. We also see that animation where it begins at point K and ends at point L. So point of contact started at the dedendum portion of the pinion, while it ends on the dedendum of the wheel. So this one is wheel and this one is pinion. So it started at the dedendum of the pinion and ends at dedendum of the wheel. So this distance travel from the start, that is point K, to end of engagement, that is L, is called as a path of contact, denoted by notation KPL, where P is a pitch point. It passes through pitch point. So point of contact can be K, can be P, maybe L, or anywhere on this path. Now for we have to define expression for path of contact, and for that the same diagram I drawn here, that is KPL is path of contact. Now the derivation, already I told you these points MN, KL, what they are, and this is animation for path of contact. You can see it started at this point, it moves along a straight line. You can see this one, and it ends here. So at this point it ends. At this is the point, or we can say this is common tangent, blue color one, cut by addendum circle. So when it cut by addendum circle, it ends, while here it will start. You can see here at this point the arrow. So this is beginning point. You can see that I'm just highlighting here. This is beginning point and it ends here. So this path is called as the path of contact. One more thing you may observe. At intermediate point, it is one pair of teeth in contact, but at the end and beginning, there must be two pairs of teeth in contact. That discuss later. So path of contact I discuss. The same animation. We have to go for derivation of this. So KL is nothing but path of contact. It is addition of KP plus PL. So KP is path of approach and PL is path of recess. So portion of the path of contact from start to pitch point is called path of approach, while portion of the path of contact from pitch point, that is P to L, that is end of engagement, is called path of recess. So approach is nothing but start of engagement to pitch point, while recess nothing but pitch point to end of engagement. So it is, we'll define here what is path of approach and what is path of recess. So portion of path of contact from start of the engagement to pitch point is called approach, while from path of contact from pitch point to end of engagement is called path of recess. And to consider derivation, what we discussed, it is known to the terms and all. So finally we can prove that expression for path of contact is, that is Kp is and Pn is. So Kp is equal to Kn, that you might remember. Kp is equal to Kn minus Pn, but Kn is this one and Pn is this one. So my final expression is Kp is equal to square root of Ra square, that is addendum wheel radius, minus R square cos square pi minus R sin pi. Remember here, path of contact is on pinion side, but to define path of contact, we have to use dimension of the opposite one, that is a wheel. So to define path of contact, path of approach, we consider dimensions of wheel, while to define path of recess, that is Pn, we consider dimension of pinion. So Kp is path of approach, which is square root of addendum radius of the wheel square minus radius of the wheel pitch circle radius, cos square phi is pressure angle, and R is a pitch circle radius. So three parameters required: addendum radius of the wheel, pitch circle radius of the wheel, and pressure angle. It is Kp, while Pn is same term, only it will be a small r, that is nothing but radius of pinion. So Ra square minus R square cos square pi minus R sin pi. Both are same expressions, only difference is to find out path of recess, that is Pn, we use dimensions of pinion, while to find path of approach, that is Kp, we use dimensions of wheel. And if we add these two, that is approach plus recess, we get expression for path of contact, that is KL is equal to Kp plus PL, which is this square root plus another square root minus R plus R sin phi. It is your expression for a path of contact. And then arc of contact is nothing but, as we seen, the path of contact is point, or I'm saying path of contact is nothing but path traced by point of contact from beginning, that is K to L. So K to L is path of contact. So when the point is moving from K to L, this point on P circle is moving from G to H. So I'm saying when this point is moving from K to L, this point is moving from G to H. So this arc travel or distance travel on P circle during path of contact is nothing but arc of contact. That arc from beginning to end of engagement during path of contact is called the arc of contact. It's nothing but a GPH. And we have expression for arc of contact by considering a small derivation, by considering the two angles. Since we consider these two angles, COD and GOH, we equate them, we get final expression of arc of contact, that is arc of contact, that is arc GPH is equal to length of path of contact upon cos phi. So to find out arc of contact, we require path of contact as well as pressure angle. And finally, the concept of contact ratio that also we discuss. So contact ratio nothing but arc of contact upon circular pitch. In other words, we can define contact ratio as nothing but number of pairs of teeth in contact. How many number of pair of teeth in contact is nothing but a contact ratio. So number of pairs of teeth in contact or contact ratio is defined as ratio of length of arc of contact upon circular pitch. Means to find contact ratio we require arc of contact, and to find arc of contact we require path of contact. So path of contact, arc of contact and contact ratio are the three terms we define here with derivation. The next topic is interference. So this topic we discuss in next lecture. Okay, a small topic remaining, that is interference undercutting and its formulas, that we'll discuss in next lecture. Okay. Hello.
Yes, sir.
Yes, sir.
Yes, sir.